Yeah, thanks everyone. Thanks so much for having me. I'm Nathaniel Rindlaub, short for Nathaniel, and I'm a software developer on the Nature Conservancy's conservation tech team. And as Steph teed up earlier, I'm here to talk about a system we've developed over the past couple of years for real-time biosecurity monitoring using wireless camera traps and some computer vision. But before I kind of like dive into the tech stuff, a little bit of context about the project. And also, for starters, I should stress that I'm going to be talking quite a bit about biosecurity, which, if you're not familiar with, essentially a term for efforts to reduce the risk of an invasive species introduction on a given ecosystem. And I'm going to be talking quite a bit about it because this kind of pairing of the wireless camera traps, the real-time images, and the automated ML inference really lends itself to this biosecurity use case. But for this audience especially, I want to just stress that I don't think that the utility of this system is limited per se to invasive species monitoring. I think there are lots of potential conservation problems or camera trapping projects in general that could benefit from this approach. So very curious to hear from you all if you have any thoughts on additional use cases that might be a good fit. The other thing I want to do real quick is sort of ground us a bit geographically. So the primary preserve we've been using as a test site for piloting the system is on Santa Cruz Island, which is, if you're not familiar, off the coast of Southern California. And it is the largest island in California at 96 square miles. It's also incredibly mountainous. It's got two really dramatic mountain ranges that are running kind of east to west, and its highest peak puts it among the tallest islands in North America. But also similarly to the kind of biosecurity thing, don't get hung up on the geography too much. I want to stress the system was not designed specifically to be used in Santa Cruz Island, on Santa Cruz Island. Same approach that I'm going to describe can be adapted and applied, we hope, to lots of different ecosystems and geographies. That said, islands are often uniquely vulnerable to invasives. So their isolation from the mainland simultaneously allows for their ecosystems to evolve and flourish in pretty exceptional ways. So of course, think like Galapagos, but because they've been sheltered from mainland threats for millennia, this also leaves them exposed and kind of fragile in the face of new species introductions. So on Santa Cruz Island, millions of years of isolation has produced a bunch of species not found anywhere else in the world, including 8 extremely rare plant species, a unique species of scrub jay you can see on the right here, and probably most famously the Santa Cruz Island fox over on the left, which are just these absolutely adorable little 4-pound foxes, and they're only found on SCI and a handful of other channel islands. And some quick history: about 20 years ago, they nearly went extinct, but some pretty bold actions by the Nature Conservancy and partners helped save them in what is now considered one of the fastest and most successful endangered species recovery programs in US history. But Santa Cruz Island, as you can see from this heat map, receives a ton of boat traffic, a ton of visitors, and also cargo really on a daily basis. And because of that, there's the potential for any number of mainland mammals to stow away in a boat, like in the hold of a boat, and make their way to shore. So cats and raccoons, for example, are a concern, and they have made their way out to other channel islands nearby in the past, but far and away, kind of the most likely invader and potentially the most damaging are rats. So why are rats such bad news? Well, they're highly resilient and adaptable, and they both outcompete and often prey directly on native island fauna, which of course has all kinds of cascading effects across these delicate ecosystems. This is an image that was taken on Anacapa Island, which is just 4 miles east of Santa Cruz Island, so a little too close for comfort. And it is kind of chowing down on one of its favorite food sources, shorebird eggs. Unlike Anacapa, Santa Cruz Island doesn't have rats and never has. But the fact that it has been rat-free is pretty anomalous. So it's estimated that humans have introduced rats to 90% of the islands in the world. And as a result, rats have single-handedly caused half of all bird and reptile extinctions globally, which is quite shocking. And probably kind of most relevant to this conversation, and also very startling, is that a single pair of rats can produce 5,000 offspring in a single year, which means that, if a pair of rats or a pregnant rat found its way out to the island, we would need to know about it immediately if we stood any chance of containing the incursion. So the question really is, how do we monitor this massive island that's 3 times the size of Manhattan, super mountainous, has no cell service for these tiny animals that don't, as far as we know, actually exist there? And so the answer is, we think this first of its kind system for real-time remote biosecurity monitoring. And it's comprised of a network of wireless camera traps, automated lure dispensers, and cloud-based machine learning platform for automated species detection and alerts. So one way to think about it is like the whole thing is sort of like a Ring doorbell for rats. So let's get into the hardware a little bit. The specific cameras we're using are called Buckeye X80s. You may be familiar with them. Buckeye's the manufacturer, X80 the model. And they are unique in that they can communicate and transmit images to one another via low-frequency, long-range radio. It's called XB Pro, if you're familiar with that particular type of radio technology. You'll also notice that they are solar powered, which means that they require very little maintenance. And our oldest cameras have been out in the field on the island for well over 2 years, I think, at this point, running nonstop, essentially without any human upkeep or intervention. The other really cool thing about them is that you can wirelessly pair them together to form a mesh network. So when an animal trips one on the far side of the island, that camera takes a photo and broadcasts it out to the next closest camera in the field. Then the cameras repeat this pattern of receiving and rebroadcasting the image up through the network until it reaches a base station. The base station in our case is comprised of a radio receiver, which demodulates the RF signal into a digital image. Image is then passed on to a fanless industrial computer. In the image on the right, this is sort of a prototype. You're going to recognize that as a Raspberry Pi, but we've kind of upgraded our system since then. And the computer is kind of responsible for uploading the image to the cloud, or specifically an S3 bucket, if you're familiar with AWS tools. But the key point here is that aside from the base stations, which serve really as the gateways to the internet, none of the other cameras or devices in the network require any Wi-Fi or cell service. So again, they communicate 100% through this XB Pro radio. So this fact, combined with the fact that you can daisy chain them together to extend their range and circumvent challenging topography, is really what has allowed us to capture more or less real-time imagery across this vast remote island, again, with little to no internet access, other than these points at which we have base stations. So that's how the camera network functions at a high level, but really at the risk of turning this into a full-on Buckeye advertisement, I want to pause and just plug a couple of the features that I think make these particular cameras pretty compelling. And I should also say, for those sort of wondering, you can probably guess that these cameras aren't super cheap. They're about twice as expensive as your typical Reconics. And for many camera trapping applications, they're almost certainly overkill. But I do think if you have need for long-term deployments in remote areas, it can make a lot of sense, and that added cost can be recovered in like staff time savings alone. So as many of you, I'm sure, are familiar in your typical...
Sorry.
Yeah.
Just interrupt. How much is it? Does it actually... We have Frank's wondering, and I'm wondering. Do you have a dollar?
It depends how much you're going to dress it up with additional antennas and like various sort of modifications, but we're in around $1,000 per node, essentially. The other thing that I'll touch on in a second is that like a lot of times, like, you're going to need to use repeater nodes in order to sort of like rebroadcast rebroadcast the images like around up drainages and around hard to get to areas, and so that can also add to the cost. It really depends on your topography and the tree canopy and stuff like that, how many repeaters you need, which of course is going to add to the cost of the entire setup.
Cool.
Yeah. But of course, as you know, with a typical SD card based camera, like, you set up the camera, you say your little prayer, and then come back however many weeks or months later, hoping the camera didn't get knocked over or the batteries didn't get depleted in the first week from, some leaves blowing like crazy in the wind. But with Buckeyes, once they're set up, of course, you don't have to return to fetch the SD cards or swap out batteries. With the real-time images, you know essentially right away when something goes wrong. So you can be a lot more targeted with your maintenance efforts. And you can, if you address those issues quickly, you're going to get much more usable data for less effort and less time. And another cool feature is that a good amount of the maintenance can be done without leaving your house or office. So because the radio communication between the cameras is bidirectional, you can configure settings, get battery status reports, you can manually trigger the cameras. You can do all of that remotely. So again, say camera's firing too much, you notice during certain hours and the wind's particularly blowing strong or is overexposed at night, you can adjust those settings right from your computer at home. And again, repeaters kind of are these unsung heroes of the whole system. The cameras themselves and the repeaters can transmit images up to 7 miles. But the repeaters we've found have been super invaluable for extending range and deploying cameras in some really challenging locations. So for example, deep in heavily canopied drainages or even in caves. So after the images propagate up through the network on the island, they get uploaded to the cloud, at which point they enter sort of the software side of the system, which we call Animl. And we built Animl to solve for another challenge that plagues pretty much all camera trapping projects. Cameras, of course, fire at anything that moves, whether it's a giraffe or a blade of grass. So they very quickly can produce tens of thousands of images, many of which aren't particularly interesting to us and we don't really care about. Animl solves for this with an automated AI workflow in which new images get piped through a sequence of computer vision models to try to essentially determine what's in them. And like all ML models, ours are not 100% accurate by any means, so the predictions still require humans in the loop to review them, but it makes the review process much more efficient. And our automated alert system means that if a rodent gets detected by one of those models, we'll know about it within minutes of that picture having been taken. And also, I think I saw Dan Morris on the chat there, so shout out to Dan and the Microsoft AI for Earth team. Their object detection mega detector is one of the models we've got integrated in the app, and they've been super, super helpful. So this is a GIF of the user interface on the left, but I'd like to highlight something that I think is really important. And that is, we designed Animl to be a scalable camera trap data management platform. And so again, its utility is not limited to any one environment or use case. Rather than building a bespoke application that is specific to Santa Cruz Island and biosecurity and our Buckeye cameras out there, this software we tried to design it to be much more of a general purpose tool. So what does that mean exactly? We decided to do a couple things. So number one, we wanted to be camera trap agnostic. So make sure that it was able to ingest data from a variety of camera trap manufacturers and types, your Reconyx, your Buckeyes, your cell-based cameras, what have you. Number two, allow for the easy integration of multiple machine learning models that could be suited for different environments or target species or different business use cases. And number three, kind of empower users to then configure customized and totally automated machine learning labeling pipelines. So for example, if you're interested in studying, a wildlife crossing, for example, it might not make sense to check those images for our Santa Cruz Island fox. They're not going to be there. So to solve for that, users can configure custom sequences of models to run against their own specific subsets of images or cameras. Of course, send automated alerts, and then lastly, offer this front-end user interface on the left here that allows users to view their images, view the predictions, validate the labels, and configure all those alerts and machine learning pipelines to meet their particular needs. This is a probably too hard to read diagram of the application architecture on the left, which is almost entirely built out and hosted in AWS. Free of charge, I should say. So huge thank you to Marco and the folks at AWS who have been incredibly generous and have donated a bunch of compute credits to help get this thing off the ground. And if you're familiar with AWS, this is on the right, a list of just some of their infrastructure we're leveraging. Obviously, it's quite a bit. And really can't overstate how much of an enabler their products are for operationalizing ML models and building out like a really fully featured production application for conservation purposes. And like I said, the goal was really not to wire up a single data processing pipeline tailored to our specific use case and location. The goal was to build a platform, and AWS kind of made a lot of the aspects of that very, very easy. Shouldn't say easy, but made it possible for sure. Before I close out, I just want to take a stab at kind of explaining why we did this. You know, it was a lot of work, to build all the custom software and these kind of like using these niche expensive cameras. But I think it's worth pausing and asking why this hasn't been done before, because as a consumer and also as someone in the conservation tech space, it can feel like we're kind of surrounded by similar technology every day. And another way of framing it, I think, is like, you know, the Ring doorbell analogy I made before is pretty apt, but like, why not literally use Ring doorbells or some other commercial off-the-shelf option? Or on the software side, like, you know, I can look at my phone and my iPhone and it'll unlock itself. Like, how hard could it possibly be to identify a rat in a grainy camera trap photo? You know, essentially, aren't these problems already solved? And I will say that when I started digging into this project a couple of years ago and started looking for some commercial off-the-shelf solutions, I really had kind of assumed they were. And if it wasn't out right now, you know, maybe we wait another month or two. But a solution never materialized, and I came to realize the reason is kind of twofold. The first is that every aspect of IoT is hard, and you all probably know this. I can't stress it enough. You're essentially running small electronics exposed to pretty extreme elements in remote places, and figuring out how to connect them to the internet is not trivial. You're extremely power constrained, right? You got to work with whatever the sun's going to give you on a given day, and by extension, extremely compute constrained, because of course it takes a lot of energy to do complex computations in the field. There's also a lot of different sort of radio technologies to choose from. So you've got cellular, satellite, Bluetooth, LoRa, others I'm sure, but there's always a really delicate trade-off between kind of the bandwidth, the range of the transmission, the power consumption, and the cost for all of these things. And for this to be viable and scalable solution, we wanted to be able to, we're going to have to deploy a lot more of these devices, to put probably hundreds, maybe thousands across remote islands. So figuring out how to do that cheaply is really challenging. And to the machine learning point, it turns out, to my surprise, but maybe not you're all surprised, that computer vision on camera trap imagery is also very hard. But it starts to make sense once you think about it a little bit. So in pictures that humans have taken, of course, which is what most ML models are trained on, and really what most pictures are, typically the subject is in focus, it's in the center of the frame, obvious what the photo is of. And if you were to go look for training data for your like teapot classifier, you could do Google image search and instantly get millions of different teapots of all different shapes and sizes and backgrounds. And that kind of sample diversity combined with the subject clarity is going to really help out a lot. Camera trap images, of course, on the other hand, subject might be 2 inches away from the camera and completely out of focus, taking up the whole frame, or 20 feet away and 90% obscured by, you know, a bush or what have you. It's just wildly uncontrolled. And what's more, your training data might include 200,000 images, but they might have only been taken at 12 locations. And so the backgrounds of the images, of course, don't change too much. They're fixed cameras. So what typically happens is the models get really good at detecting animals in very specific locations. And as soon as you point the camera elsewhere, the performance tanks because the models have learned too much about the background and can't really generalize. So it's just hard, and I'm not going to pretend like we've nailed it. There's a lot of room for improvements in our models. But one of the early decisions we made was to focus on building out the platform that would essentially allow us to easily bring online new models and integrate them with our existing data stream so that we could rapidly operationalize new developments in the computer vision space. In closing, again, cannot stress enough how important rapid invasive species detection is in the context of biosecurity, both from an ecological perspective, but also a financial one. So that rat photo from Anacapa that I showed earlier, they were eradicated in 2001, but at the tune of $5 million. And Anacapa is tiny compared to Santa Cruz Island. It has an area of 1 square mile versus 96 square miles. So in the context of safeguarding the pretty historic conservation victories on the island, investing in prevention and early detection is money extremely well spent. And with global warming, resource scarcity, and globalization all on the rise, there are many, many other islands with flora and fauna not found anywhere else in the world that are more vulnerable than ever to invasive mammals. So we see the Biosecurity Network on Santa Cruz Island as a model for cost-effective remote monitoring at scale. And our focus now is improving the models, working with partners to demonstrate efficacy, in new geographies, and catalyzing adoption at regional and hopefully global scale. Very last slide. Thank you all very much for your time, and would love any feedback you might have, other conservation use cases that come to mind that might be applicable, other products, people working in the space we should be talking to, any blind spots or assumptions that you can help point out. All of that extremely helpful. So feel free to share your thoughts in the chat or questions in the Q&A, but don't hesitate to reach out after the call either. So thank you very much.